Have you ever really stopped to think about it? That incredible, completely invisible journey that power takes just to get to the socket in your wall. Well, today, that's exactly what we're going to do. We're tracing that path, from the very moment electricity is born, all the way to your home.
I mean, it's something we all take for granted, right? You plug in your phone and it just works. But the system that makes that simple little act possible, it's one of the most complex and amazing machines humanity has ever built. So let's break down how it all really happens. All right, let's dive in. Here's the roadmap for our trip. We're going to start where power is born. Then we'll jump on the electrical superhighway, see how all that traffic is controlled, and follow it right to your front door. After that, we'll touch on how we pay for it all. And finally, we'll take a peek into the future of the grid. Okay, so first things first, our journey has to begin at the source because, you can't create electricity out of thin air. It has to be converted from another form of energy, whether that's the intense heat from burning coal or the powerful force of the wind. And when you boil it all down, we really rely on two main families of energy. On one side, you have your renewables, things like hydro and wind, which, as the name suggests, naturally replenish themselves. And on the other side, you've got the non-renewables, coal, natural gas. These are finite resources that we have to burn to get the whole process started. And here's the cool part. Whether it's burning coal to make steam or just using the raw force of the wind, the basic principle is often exactly the same. The whole goal is to create motion. You need to spin a turbine, which then spins a generator. And it's that generator, that final piece of the puzzle, that converts all that movement into the electrical energy we actually use. So great, the electricity is generated. But honestly, that's only step one. Now we face a truly massive challenge. How in the world do you move that power from some remote plant all the way to the cities and towns where people actually need it? Well, you need an electrical superhighway. But there's a problem, and it's a fundamental law of physics. Whenever current flows through a wire, some of that precious energy just gets lost as heat. And the longer the wire is, the more energy you lose. It's kind of like trying to carry water across a field in a really, really leaky bucket. The solution, though, is absolutely ingenious. To send the same amount of power but lose way less energy to heat, you have to lower the current. And the way engineers figured out how to do that is by dramatically cranking up the electrical pressure, or what we call voltage. And when I say that crank it up, I mean they use extreme pressure. Just to put this into perspective, a power station might generate electricity at around 25,000 volts. But for its long journey on the grid, it gets stepped up to an incredible 400,000 volts. That is thousands of times more powerful than what comes out of your wall socket. And this super high voltage, well, it's the secret sauce for the entire system. By slashing that energy loss from heat, we make it not only possible, but actually affordable to move huge amounts of power over hundreds and hundreds of miles. All right, so now we have this massive flow of high voltage power racing across the country. But how do you safely get it off the superhighway? How do you direct it to one specific town versus another? That is the job of the grid's traffic control system. And all of this happens at a substation. You've definitely seen them, those complex spider webs of switches and structures. The best way to think of a substation is like a major highway interchange. It takes that bulk power from the main transmission lines and starts the process of stepping down the voltage to levels that can actually be used locally. Now, this step-down process doesn't happen all at once. Inside that substation, these giant transformers reduce the voltage in stages. So they might take it from that crazy 400,000 volts down to 33,000 volts to send out to a big industrial park, and then maybe down again to 11,000 volts for our local neighborhood networks. Of course, working with this kind of power is incredibly dangerous, so safety is everything. Before anyone can do any maintenance, there's a super strict procedure. First, a circuit breaker flips, stopping the flow of power. Then, an isolator switch is opened, and this creates a visible air gap so workers can literally see that the line is disconnected. Only then is the equipment grounded, and only then can the work begin safely. So, we're on the final leg of the journey now. The power has left the superhighway, it's passed through the major interchanges. Now it's time to bring it down the local streets and right to your front door. This is what they call the final distribution system, or the last mile. That green box on the curb or the transformer up on the utility pole, that's what's performing the last crucial step down. It delivers a heavy-duty 415 volts for industrial users, and finally, a safe and usable 230 volts for all of our homes and small businesses. Now, this entire incredible feat of engineering, from the power plant all the way to your plug, it has to be paid for, right? So let's take a quick look at the economics behind your electricity bill. The cost of your electricity is basically split into two big buckets. First, you've got the capital charges. Think of this as the massive upfront investment it takes to build the power plants and all those transmission lines in the first place. And then you've got the running charges. That's the day-to-day cost of fuel, paying the staff, and just keeping everything maintained and repaired.
A really key idea here is something called the load factor, which is basically an efficiency rating for the entire grid. Think about it like a highway. If traffic is steady all day long, that's pretty efficient. But what if it's empty most of the day with just one giant traffic jam at rush hour? That means you've built this huge, expensive highway just for that one peak. A low load factor is the same thing. It means we're all paying for a bigger grid than we usually need. And that idea of efficiency brings us perfectly to the final part of our journey, the future. Because as we move toward more renewable energy, the grid is facing a brand new challenge, and it's one that's going to require some amazing new technology. This, right here, is the fundamental challenge with so many renewables. Unlike a gas-fired power plant that you can just turn on and off whenever you want, sources like solar and wind, well, they're intermittent. So how do you keep the lights on when the source of your power is totally unpredictable? The answer is energy storage, specifically something called secondary energy storage. You can think of these installations as a giant grid-scale rechargeable battery. They're designed to soak up all the excess energy when the sun is shining and the wind is blowing, and then feed that power back into the grid when we need it most. And the process itself is beautifully simple when you think about it. First, you have the charge phase, where the system just soaks up all that surplus power. Then it simply stores that energy. And finally, when demand is high or the sun goes down, it enters the discharge phase, releasing that stored power back to keep the grid stable. So, from a spinning turbine all the way to a stored electron, the journey of power is just an incredible story of physics and engineering. The system we have today is truly a marvel, but that journey isn't over. As we look to a future powered by renewables, the next chapter is going to demand even greater innovation. It's going to take a lot to build the smarter, more flexible, and greener grid of tomorrow. Thanks for coming along on the journey with us.